Hi, and welcome to the Special Situations cast. My name is Bram de Haas. I run the Special Situations report, which you can find on Seeking Alpha. Before we jump into the interview with my guest of today, I want to make a few things clear. Nothing on this show is investment advice. It's for entertainment purposes. Either me or my guest may have positions in any stocks or securities that we discuss. So keep that in mind, and please go and enjoy my interview of today.
To add the first 50 results is exactly the time it takes to calculate the next 25 and the next 13 and the next 6 or 7, right? So we've got some odd numbers there, so it gets a little bit messy, but not much, right? So there's another technique that's used in all CPU chips and all FPGAs called pipelining. And it's kind of weird. A pipeline is a brick wall put in the way of the calculation. It says stop at this point. And what it does is it says everything leading up to that has to complete where that brick wall is. And then you drop the brick wall and everything progresses to the next stage. So what you do in that, and I'm sorry, this is sort of really getting, there's a whiteboard behind me, maybe I should draw it. What you end up with is after those first 50 adds, you put a brick wall there, and the reason you put it there is that on the other side are the 50 results from the prior cycle. Okay, when I first described that tree, you can't start the second row of adds, right? The first row of adds is 50 adds delivering 50 results. The next row is 25 adds delivering 25 results. But those 25 adds can't start until the 50 adds complete. But if I put up a brick wall between each one, then each one can run independently with the result from the previous cycle. So think of it as the brick walls are staging the data in a pipeline. Let me think, how would I better describe that?
But if you maybe give us some practical examples of...
Okay, well, I think I'm getting to where this makes sense. The reason that the little brick walls make sense is because they let you start the next calculation. So let's take that 100 adds. If I have to do the 100 adds one after the other, it takes me 99 cycles, right? If I do it, or rather 99 times, right? I do the add and then the next number comes, I do another add. If I do the 100 numbers at once into 50 adders, then 25, etc., that tree of adders is about 7 deep. And so it takes 7 cycles or 7 add times to get a result at the bottom. So you've gone from taking 100 cycles, right? We assume that all add operations take the same amount of time, right? Then it takes only 7 100ths, right? 7 cycles to get to an answer with the tree structure versus the do the numbers one at a time. If I put brick walls between each of those rows of add operations, and each one takes 1 cycle, the row below it also takes 1 cycle, but it's working on the result from the previous cycle. This is kind of tough, I understand, with my arms waving around here. You get an answer.
It's great. I think it's super helpful because then, I mean, if you will next move on to giving us like the practical examples where it's then applied, then I think we can put it in a framework.
Okay. Right. So let me give you the TLDR, the too long, right? Because I'm taking too long to explain it. When you add these brick walls, the correct term is a pipeline register. That's the technical term. when you add these registers, they basically schedule the calculations through this tree. And what it lets you do is every cycle, you can put 100 new numbers in at the top and get a new result out the bottom 7 cycles later. So let's say you have 1,000,000 of these 100 numbers. So you have 1,000,000 sets of 100 numbers. It takes 7 cycles to get the first answer out. It takes 1 cycle to get the next answer. It takes 1 cycle to get the next answer. And so what happens is you have a delay for the first answer of 7 cycles, which is just a function of the complexity. But then once you've started, you can then get new answers every cycle. And so now you've got a situation where if you only had 10 data sets of 100 numbers, this wouldn't look very impressive, right? It'd be an improvement, right? But it'd be an improvement over doing the adds one at a time, right? If you had 100 sets of numbers and you're going to add them up 100 at a time, right? Then it takes you 100 cycles for the first set, 100 for the next. It's going to take you 10,000 cycles to do, because you've got 10,000 numbers to add up 100 at a time. If you do this tree type thing with all those extra adders, it takes you 7 cycles for the first result, and it takes you 1 cycle for every other one, for every other result.
Mm-hmm.
And so you will have your 100 totals in 107 cycles. So you've gone from 10,000 cycles down to 107 by building a custom adding machine.
And,
right? Okay, so let's go look at an inference problem, right? So an inference problem is you have a data set, millions of data sets, which all have to go through a complex calculation.
mm-hmm.
If you do that on your multi-core processor, each core can deal with 1 set of data, right? So with a 16-core processor, you can probably do inference 16 times faster. But that's the limit over a single thread.
Yeah.
If I build an FPGA and I build a custom inference engine for this specific AI, regardless of how complex it is, I throw more and more FPGA resources at it so that I can get it down to some number of delays until I get my first answer, but I'll get all the rest of my answers 1 cycle later, right? And so the bigger my data set, right? So let's say I'm training it with 1,000,000 data sets, right?
Yeah, but like a GPU would be better at this if it wasn't customized, if nothing is customized. But once you customize the FPGA for this specific task,
it would depend. Well, so the GPU will help you, but there are limits. One of the limits is how data gets to all the GPUs, right? So if the GPU chip has a pile of pins on it, right, and there are going to be issues of how does the data get to it and how does it deliver its results. And so for many applications, that data in it, right, the input and output data ends up being the limit, right? For FPGAs, just like you can customize how it does its calculations, you can also customize how the data moves. And so you can
I'm
build.
sorry, could you repeat that? Because
okay, so for an FPGA, just like you can customize how the calculations happen, because the FPGA it's like a Lego set, right? An FPGA is like a huge number of building blocks, and you can build anything you want by just putting them together. So my example of that tree of adders is a trivial thing to do with an FPGA. It's impossible to do with a CPU or a GPU unless it's built in, right? So if let's say at the beginning of your designing your computer, you didn't know that that would be the problem you wanted to do. So your processor chip and your GPU chip didn't include what I would call a tree adder because of that tree structure.
Mm-hmm.
The FPGA also didn't know that the tree adder is going to be something that's really important.
Mm-hmm.
With the FPGA, a year after you ship it into a data center, someone can figure out that a tree adder would be a great thing, and they can then deploy the appropriate information to make the FPGA do that function. Right? So that's the compute side of it. The other side is data movement.
All right.
Right? And again, the data paths in the CPUs and the data paths in the GPUs, they're basically fixed. Right? They're whatever the designer figured are the reasonable ways data will move within those devices. In an FPGA, that's customizable as well. And so, for instance, to make my example work, right, for processing 100 numbers at once, you have to have a memory where you can read 100 numbers at once. That's not a normal function, right? But in an FPGA, you can build that, right?
Right.
So the biggest thing that holds back FPGAs is you need to have really good skills at looking at a problem and seeing how to change the way you approach it, right? If the only way you think about creating, let's say I talk to 100 people and I say, I have 100 numbers, calculate the average, right? Then almost every person you speak to will say, start taking the numbers one at a time.
Mm-hmm.
Right? Not too many people will say, take all 100 numbers and add them as 50 pairs. Right? So there's the need, so the difficult problem, and it takes being exposed to the concepts and being immersed in having to rethink the way you do things, is recognizing that there's more than one way to solve a calculation problem. And that applies to...
So is it fair if I summarize this?
Please.
That
I'll probably talk too long.
We can actually, maybe FPGAs are even way underutilized, and you can customize them to do something way better than a CPU or a
absolutely.
GPU could do.
Yeah.
If you invest in the customization.
Right. Yes. Well, in fact, the only way to use not the only way. So up until the web companies, or rather the server companies, cloud companies, I guess is probably the most accurate way, up until they started deploying FPGAs, the only way FPGAs got implemented, well, only is too strong, almost only way, was someone would design an FPGA into a product, and then some engineer would have to do that customization job. And there are far fewer engineers than programmers out there. So the big advantage that the GPUs and CPUs have is you program them with normal computer programming languages, and there is a vast pool of programmers who all know how to program linear algorithms. Mm-hmm. Right? What's pretty much missing is a huge supply of programmers who know how to take what is basically a linear algorithm, do one thing at a time, and figure out that there's a totally different way where you do stuff in parallel. Now, so that's up until the cloud companies started deploying FPGAs. What they are now doing is they're now saying, look, there's this resource called engineers, right, who know how to do this really complex parallel custom computer design. Let's package that up and make it available just like buying a computer program. And so you can go onto Amazon Web Services, and not only can you get access to a server that has FPGAs built into it, but Amazon has a marketplace where companies that develop the programs can develop FPGA designs, and so you can not even know how an FPGA works, right? Ignore everything I've said for the last, oh God, hour or whatever, right? Ignore all of that and just say, go find, so let's say you want to do, say, a high frequency trading algorithm, right? I don't know if
Yeah, that
that's a
was
good
exactly
example.
what I was thinking of, actually.
Okay, fine. So you can go, so to be honest, high frequency trading demands that you have very high performance access to the trading floor data, right? And I don't know enough about that domain to know if that's something that everyone has access to. But there are algorithms where you look at the current price, the trade, right, the futures, the histories, who else is trading, right, all of that, and you want to calculate that as fast as possible on hundreds or thousands of stocks concurrently. Does that sound familiar? Right?
That sounds very
Fine.
familiar.
So let's say you're a company that really isn't set up to do high frequency trading, but you are a company that's set up with engineers who know how to take algorithms and convert them into highly parallel designs. So they can create a program and put it up on Amazon Web Services available workloads that you can take advantage of. And then I think Amazon lets the end user, right? So you have the company that's doing the high frequency trading and wants to use Amazon servers and this mystery company's program. And so that company will pay money to Amazon for the use of the server, and they will pay money on a per use and probably by the amount of time that they use it for, right? And so, they might be charged 10 cents a second, right, for use of that program. And they're charged 25 cents a second for use of that server. And I'm pulling those numbers out of thin air, right? So I don't know what the numbers are, but that's the business model for Amazon, is they provide the servers and they provide a marketplace for software that runs on their servers.
No, but this is super interesting, and I think I finally understand. Like one takeaway I got from researching Xilinx was that because there goes so much customization into these chips, that once you have your customers on board, they can't easily switch over to like Altera or.
That's correct. Yeah, it's almost impossible to do that. It isn't impossible, but it's really, really tough. And it's actually made of two pieces. One is the design that you've done. Almost, if you've done a good design that leverages everything that Xilinx, so the Xilinx and Altera chips are very, very similar, right? They're made out of the same bucket of sand, right? Sometimes even built in the same foundries, and the Lego blocks all look very, very similar.
Yeah, but it's the software and
the design tools, precisely.
Yeah.
So the design tools are radically different, and so and this is to the detriment of both companies, and the reason that FPGAs, you mentioned earlier, they seem to be really a niche and they haven't really taken off. The reality is the FPGAs have grown every year forever, right? They've always been a growing market, but the growth is slow compared to some other products. And the reason is deploying FPGA solutions is really hard because you need this limited resource called engineers, and the tools suck. They have always sucked, right? They're very difficult to learn and they take a long time to be proficient.
It's sort of comparable like the early days of programming, that they were like
much worse. much worse. No, they are really, they represent hundreds of engineering hours of developing that software, actually probably in the thousands of man years. Thousands of man years have been invested both by Altera and Xilinx, right, to develop their tools. Even so, they are a royal pain to work with.
Yeah, right? But this means that high frequency trading company is forever buying our Xilinx chips. So,
Oh, absolutely. Well, or using the Xilinx product sitting on Amazon Web Servers, right? So yeah, so the problem is so you have this limited resource called engineers
yeah,
who hopefully know how to make use of an FPGA. They have to invest literally years learning how to use the Xilinx software. And so the barrier is not so much that the FPGAs are different between the two companies, it's that the tools are different enough that if you want to switch from one company to the other, you'll have to invest more years, during which time you will be unproductive. And so typically by the time an engineer has become productive with one of the two vendors, then they will then just stick with that over and over again.
yeah,
And Xilinx did a better job of tying in engineers by making their software available, functional versions of their software for free. Right? So they charge for some of the high-end stuff, but the entry-level version of all of Xilinx's software is available free on the web. And so, and you know, Xilinx also has an active educational program that indoctrinates college students with the Xilinx products.
all
Right.
right. I think I've seen about these programs, and I think they make the hardware available, or
Right, yeah.
yeah.
So, you know, Xilinx has, I mean, Altera has too, but they just didn't do as good a job of it. And so, you know, if you go looking online for FPGA training courses,
Mhm.
they're almost all Xilinx, right? And
Right.
so what happens is Xilinx has done a much better job of growing the community of people who know how to use the chips.
Yeah,
And from my limited reading, right? So this is, as I said, sort of, I'm kind of drifting into retirement now, so I don't have my finger on the pulse, but you know, from the articles I read in just the normal engineering magazines, Xilinx seems to have put a lot of effort into dealing with the problem that engineers previously were the only people who could make good use of it. And so there's now new generation software developed by Xilinx and probably by Altera, but I haven't read about it. But also these cloud companies are doing their own development work. For instance, I know that Amazon has developed their own software to make using their FPGA in the cloud offerings easier to use. So the problem of programmers not being able to make use of the FPGAs is being solved. So they have finally recognized this is a bottleneck. And while I guess, what's the right word? The right
so,
word
so we
escapes me.
don't know for sure, but this
Right.
could be like an inflection point in the use of FPGAs.
Yeah, I would expect it will definitely ramp up as more services become available on the cloud, and more people learn that with the FPGAs, the key thing is you have to understand your algorithm and be
Yeah,
willing to take a different approach to solving it. And when you do, the opportunities, I mean, I've been working with FPGAs for 30 years, and I've seen more than a very large number of examples where FPGAs are used to accelerate things by sometimes only 10x, which is more than enough, but I've seen things where it accelerates it by 1,000 times, right? And a 1,000x improvement is pretty hard to not notice, right?
right.
So, I think the software development and basically what they need to do is make the FPGAs more accessible to the much larger programming audience than what traditionally has been used, which is the engineering audience. And I should
If I,
point.
if, if I hear you correctly, this also means that Xilinx has been like investing a lot into education. It's a little bit like Adobe. I think they gave away so much product to students for like
Mhm,
a very long
right.
time. And
Yes.
at some point, every student has been trained with Adobe Photoshop,
Right.
design students. And it's
Hmm.
the same with like AutoCAD, I think.
Yes. Oh, a lot of companies have figured out
Yeah,
that the time to indoctrinate your users is when they're a captive audience,
yeah,
and there's an educator who would love to avoid developing a course if someone will just give them a course to deliver,
sure.
right? And so the sort of stuff that in fact AutoCAD I know about, and also Xilinx, they don't just um, try to motivate it. They actually develop course material, so it's they deliver it to the educator and say, here's the course. You don't have to develop it. You just have to present it and mentor the students through the process, right? Um,
Cool.
we have talked extensively about FPGAs for compute. It's worth noting this was never their original product, right? This was never the original goal, right? The FPGAs were designed initially as a general purpose solution for general electronic system design, and that still is the dominant use, right? Although we
All right.
focused entirely on the, how does it accelerate compute? How does it work with web servers,
Yeah,
inference? This is all a new growth market that is in absolutely its infancy, right? And as more people understand the upside of taking advantage of the flexibility, right? This is something that has nowhere except up in terms of growth. Meanwhile, there's all the traditional use. I mean, when people look at design and say, well, it hasn't grown as fast as AMD, and it only does, $3 billion, dollars of business. That $3 billion of business is not on any of this compute stuff, right? It's on more traditional stuff like cell tower base stations, right? So for instance, right, you look at cellular, and the high volume is the handsets, right? And FPGAs do not belong there, and they never will be in the handsets. But the base stations, right, that infrastructure which sits there for 10 years, and then they go from 2G to 3G, 3G to 4G, 4G to 5G. Each one of those is a change of standards. And if there are FPGAs in the cell tower base stations, and there are in all of them, they can deploy these new radio systems without having to take out all the hardware. They have to change some stuff, but a lot of it, all they have to do is have the engineers create new designs that load into the FPGAs that are already there. And when I used to be an active consultant, I often had customers asking me about, how do they decide which FPGA to use and whether to use one vendor over another. And because of my history, I always told them up front I was extremely biased towards Xilinx, because that's where I'd invested all my time, learning as a designer of them, and then a designer with them. That the one of the ways to look at FPGAs was it was an insurance policy, right? The act of designing an FPGA, which initially might be a more expensive solution, right, into your product, right, was you were buying insurance, because you could screw up and make a mistake and still come back later. The best, the
but it
best
sounds like ideal for things like self-driving cars.
right. In fact, I would say, so for 20 years as a consultant, I've told people that, aside from my explaining it as an insurance policy, that the place where FPGAs stand apart from any of the more traditional custom solutions to building hardware is in the domains where the standards are not yet set or are in flux. So, for instance, and this actually even surprised me, the early rollout of digital TVs, right, when we moved away in the US from NTSC to the new, high-def TV standards where it went all digital, those standards were in flux for a decade. And so there are TVs, which is a high volume market. Well, initially not high volume for those new generation, but there were TVs that were shipped with FPGAs in them, which surprised me. But that was because the standards were changing. And so as the standards changed, the TV vendors would put new firmware up on their website that you could download, right? Stick on a USB stick and stick it into the back of your LCD TV, and it would then handle the latest upgrade to the video coding that the FPGAs were doing inside the TV. Right? Now, I think at this point, the TV standards have stopped changing, right? And so now the FPGAs are no longer used in current, new TVs. But, any place where you see standards changing, so the networking.
Yeah, and the products have to have a little bit of a life, like a lasting life, because then it's higher chance that you'll have more cycles of software.
Right. So
maybe yachts, drones, thinking of vehicles.
Yeah, I mean, and so the whole thing about self-driving cars, is an AI problem, right? That needs real time. You need an insane amount of training, right, which is ongoing, and then you have an inference engine which has to be deployed in every car, right? And if that is something that needs a lot of parallel processing and you still haven't settled on exactly what your algorithm is, and since self-driving cars are not yet a done deal, right, no one has it, that means everybody is still changing algorithms. That probably means they all have FPGAs in them. I mean, I don't know because that's not a domain I work in, but I understand the computational complexity, and I understand that the algorithms are still changing, and that is by far one of the strongest arguments for reconfigurable hardware, which is the term for, well, actually that's a specialized term, I'll take that out, but I should point out that this updating stuff, of course, is not unique to FPGAs, right? You have it with normal CPUs, it's called a software update, right? And you have it with GPUs as well, right? The difference being that for the GPUs and the CPUs, while you can update the software that they have, the hardware is whatever it was when it's shipped out of the factory. For the FPGA, the program that you upload changes the hardware, right? I mean, for my trivial example of adding 100 numbers as fast as possible, right? Let's say the algorithm decides that you need to add 200.
Sort of exponentially improves like the chip if you can match it with the right
right. Yeah, I mean the
algorithm for the job.
Yes. Well, yeah. I mean, that's the skill of taking your algorithm and figuring out how to make it parallel so that it all executes. It executes in minimum amount of time, and that works best if you have multiple sets of data that all have to be processed the same way. So if you think about a car driving down a road, you have video systems that are busy collecting data continuously, and the scenery is constantly changing. So the very first thing it has to do is do something called feature recognition. So it has to look at colors and shapes and orientations and just pick out, well, that's probably a person, that's probably a wall, that's probably a traffic sign, right? So there's just a whole lot of stuff of just recognizing objects, and that's in a scenery that is continuously changing, continuously different lighting conditions, right? Other vehicles around you screwing things up, right? So I would expect the brilliant people who are working on that haven't come up with a single right solution. And so they're exploring that and being able to build custom hardware, right, without having to, physically build another board, but all you're doing is loading a new program into an FPGA to rearrange the Lego blocks. That that gives you flexibility at a cost, right, that the GPUs and the CPUs can't do. I mean, they can change the algorithm, but they can't change the hardware that implements the algorithm. The FPGAs can.
Yeah.
Okay.
So maybe should we go over what they're bad at or what their drawbacks are?
Sure. So FPGAs, so let's say you've got an algorithm where you've stopped making changes, you're confident you don't need to make changes in the future, and you're going to go into volume production for whatever application, right? So now you no longer need the flexibility or the insurance policy that the FPGA offers. Okay, so now if your volume is, you know, under 100,000, you probably stay with FPGAs anyway, because the cost of converting it into a custom chip, right? Now the custom chip the actual chip itself might be 1/10 the cost of the FPGA, right? But that's
Yeah, but
just
you have
the
to
cost
set up the production line.
Right. So, well, there's the whole engineering of building a custom chip, and that can run for the types of things that we're talking about, right? For these high-end compute-intensive challenges, right? We're talking about engineering efforts that probably run between $10 and $100 million, right? So, if you're at the high end of that at $100 million, and you're only going to deploy 1 million copies, that's $100 adder to every instance.
Yeah.
Right? Which means you stick with the FPGA, which is why Xilinx is big in automotive, is you're not shipping 100 million auto navigation systems that are identical, right? You've got every different model of car, you've got different vendors, right? All the different car manufacturers, they're all doing their own stuff, right? And they're dealing with algorithms that...
robots.
Beg your pardon?
It sounds like a great solution for robots.
Yeah, well, Tesla has certainly decided that. But the algorithms are still being changed, right? They're still rolling out updates. But you wanted to know where an FPGA is not a good solution.
Right.
So let's say you've got a situation where you've stopped making changes and you're happy with your solution, right? It's probably, let's say it's a TV, right? The standards have settled down and they're no longer changing the different video systems. Everybody has decided that 1080p is the way to go, and you don't have to support the other 30 standards that also have been around, right? No one needs 360 sequential, right? Everyone goes 1080p. Fine, you build a chip that just does 1080p, right? And you pay the $10 million engineering charges to get it developed, and then you make tens of millions of them, and you amortize that engineering cost at $10 or less per chip, right? For a chip that maybe sells for $20 or $30, right? So the advantage is the chip will be 1/10 the cost. It will draw less power. And
it's maybe interesting to go over, because the FPGAs are less power efficient than if you have a, you would call that maybe an ASIC.
Yeah, an ASIC is, well, ASIC or custom chip. I use the terms pretty much synonymously. So the flexibility that the FPGAs have comes from having extra stuff on chip that is there primarily to implement all the stuff to let you connect the blocks any way you want. I mean, when you look at CPUs and GPUs, the interconnect between the different parts is just wires that are part of building, part of building the chip. In the FPGAs, there are switches that are used for switching between different wires. So all the interconnect in an FPGA is made up of lots of little separate pieces of wires and then switches that can be then used to connect them together to create the connections. And in terms of the physical amount of the chip, more than 75% of it is the switching logic. So 75% of the chip is delivering flexibility, not delivering adds and multipliers, right? Whereas if you go look at a CPU chip or a GPU chip, probably 10% of it is exclusively interconnect, and the rest of the interconnect typically is on an upper layer on top of the functional stuff, which might be the adding and multiplying or other functional units that are at the lower levels of the chip. So the actual use of the chip, the physical size of the chip is totally dominated by functional logic in GPUs and CPUs, whereas in FPGAs, about 75% of it, approximately, is this flexibility part of the chip, right? Which means that it's much more expensive for a given amount of computational capability. The difference being that the FPGA lets you reorganize that functionality, right? So the main thing is the FPGAs are more expensive and they require more power.
So they're also more expensive, during use. And is it?
Yeah, well, they draw more power,
Mm-hmm.
so that's an expense. They physically are probably bigger, which means they take up more board space on the circuit board. They probably get hotter, which means you may have more cooling issues, right? Although the CPU guys seem to have really figured out how to make chips that really get hot.
Okay.
And need big heat sinks and fans. So, the FPGA guys are kind of in the same area.
Now, is there like a huge difference? Can you quantify it a little bit, or is it impossible depending on?
It really depends. It depends, but I would guess. It would be a total guess, but I wouldn't be surprised if FPGAs, just for a given size, maybe draw twice as much power as something that was custom built to do the same function.
Sure. Well,
right?
Thank you for that guess. That's
that's.
And now I know it's probably not 100 times or 10 times.
No. It's the ballpark is probably down around 2 or 3, right? So it's of that order.
Yeah. That is cool.
Yeah, there's a lot of interesting business reasons why Xilinx and Altera were successful with chips that sometimes are only used in relatively small quantities. There are companies that only build 10 of something, right?
Yeah, but the way you've explained to me how they work, in what kind of process they're used, and how sticky that customer will be.
Right.
I really like this whole idea, and it's kind of unique in the semiconductor where with other chips is often who's the leader and everybody switches to the leader, and then it's difficult to lose the leadership, but that's another story.
Yeah. There have been many FPGA companies and many companies that were existing semiconductor companies that tried to do FPGAs as well. And they're companies you've heard of that have tried to do FPGAs and have failed. And the companies include AMD, Intel, and I'm not talking about Intel with Altera, but Intel a few decades ago tried to do FPGAs on their own. Texas Instruments, National Semiconductor, Motorola, have all tried to do FPGAs and have all failed at it. And the reason is that barrier, the term, at least when I worked at Xilinx, was barrier to entry, right? Which was a function of the very complex software and the investment time it took for an engineer to learn how to use the tools. And there's something else.
Businesses that that maybe they don't grow so fast, but it's so you have to invest for so many years, and somebody can't start right now
Right.
catch up in 3 years. It's
Yes.
impossible.
It's certainly impossible to predict.
Yeah, like
Yeah. I mean,
like a real
I would.
disruptive
Yeah.
change.
I'd like to go back a few years and buy Xilinx back when it was down at 50. It wasn't that long. It was 3 or 4 years ago. And I should say, I am.
Maybe it gets back there. You never know.
Well, it could, but I rather like it up at 120, approximately. And for those who are listening in, I am long Xilinx and have been since 1990.
Cool. And AMD or
I did have AMD stock, but I sold my AMD stock 30 years ago.
okay.
Yeah, I sold my Xilinx. Yeah, I sold my AMD stock when I joined Xilinx.
Oh, sure.
Well, at that point, it was just break even, and it was a very different company.
No, hey, but I think it's great if you work somewhere to have the stock. It's maybe not every financial advisor would say, but especially if you're as a growing company, you really want to be part of it. It's cool.
Right. Yeah.
And let's see, what did you think of this potential merger or acquisition? Did it surprise you?
Yeah. Absolutely, total surprise. I mean, there's been rumors of Xilinx being acquired ever since Altera was acquired. Right, there were predictions that Xilinx would be snapped up immediately, and that was 5 years ago. This most recent, I guess, leak, since I don't think there's been any official announcement yet, right?
No.
Okay, so if it's only a leak, everybody seems to be taking it more seriously than the other stuff, which I think was much more speculative. But there were previous suggestions.
I can say a little bit about the dynamics of leaks and stuff like that. A leak is actually a little bit bad for the odds of a company being acquired because it drives up the price, and sometimes a buyer thinks, never mind.
Right, and then the price falls over.
Yeah. And usually rumors don't pan out. It depends a lot on the source. This is a really good source, Wall Street Journal. And if the market responds really strongly, as it did in this case, that's a good sign. Or then they're more often successful. But usually they don't amount to a deal.
Right.
But
I've been watching Xilinx and enjoying the roller coaster for a very long time, and so I mean, last year Xilinx peaked at 140, right? The day before Mr. Trump said no more shipments to Huawei, right? Which was followed by Xilinx falling over pretty severely, and it's just now starting to come back up. I've noticed that the price that Xilinx is now at, basically, if you multiply that by the number of shares, matches that 30 billion. Right? So Xilinx, so basically this run up over the last, basically on Friday, basically totally took on board that 30 billion number, which I don't know how that plays out if the acquisition goes in, since usually you want to see the acquisition at some premium above the current market price. That would suggest that if it did go ahead, it would be at a number over 30 billion. But I mean, we are now way out of my area of expertise or knowledge. But you asked me, what do I think about it? So I'm going to put aside entirely the business case for it for the moment, because I have no clue what AMD will do with Xilinx. I will observe that so I've been involved with FPGAs for 30 years. So I was there not at the start, but was there before Xilinx was a public company, right? When Xilinx was only 4 or 5 years old and was just barely becoming profitable, right? So I've been there for the whole ride, and because of my job function, part of my job was to look at every other FPGA vendor and make sure we built better FPGAs, since that was my job title: build better products than the competition. Didn't actually say that on my business card, but it was close enough. So I've watched every major semiconductor company, and I just rattled off a few of them, but there were more. Over the last 30 years, there's been in excess of 30 FPGA startups, either within companies you already know about or companies that got funding, flew for a few years, and either got acquired or got burnt out. And here's what I noticed. For the companies that were totally independent startups, they never got over the barrier, right? Currently, there's only one that seems to be getting some traction. It's a little company called Acronix, but in the grand scheme of things, they represent at most 1% or 2%, right? I mean, I don't know that number, again, pulling that number out of thin air, but I've bumped into a total of 0 people who are using their product, right? On the other hand,
and company Lattice, I've seen that mentioned.
So the pecking order has changed a lot due to acquisitions. But if I go back a few years, because there's been a few acquisitions recently that have shuffled things around. But if I go back a few years, here's what the pecking order used to look like. Xilinx was number 1 with more than 50% of the market, right? And that's true for at least the last decade. Right? Altera was number 2, and they held maybe 35% of the market, right? So, and again, I'm pulling the numbers out of thin air, but if someone goes and checks me, I'm going to be within 5% of the right numbers, right? So Xilinx was at about 50, Altera was at about 35, and the remaining 15% was split among several companies, one of which was Lattice, another one was Actel, and those were the two major ones remaining. So Actel got acquired, the company that acquired it got acquired, the company that acquired it got acquired, and so the products that used to be Actel have ended up inside a company called Microchip. So the Microchip FPGA offering is a hybrid of the traditional Actel product line and a product line they acquired before they themselves got acquired, right? Altogether, that probably represented maybe 5 or 6%. Lattice still, I think, is independent, right? And they probably represent 6 or 7%, right? Even today. And Lattice has not even tried to attack the high end. So Lattice, as far as I know, is a non-player in this high-end battleground that Altera and Xilinx are fighting for with these massive cloud accelerator type products, right? And just the general high-end FPGAs. Nevertheless, Lattice is a successful company and has an FPGA product line, some of which dates back to the AMD. Well, in fact, part of it actually is, remember I said that AMD tried to do FPGAs? They spun it out as a separate division, and then that division was acquired by Lattice. Right? So the Lattice FPGA technology, some of it was homegrown, and some was through acquisition of AMD's business. There was also Intel's.
So, Philip, you're maybe a little bit biased, but
absolutely, I'm biased.
How much would you say Xilinx is ahead of maybe Altera as most importantly?
From a technology point of view or a business point of view? From a technology point of view, they're equal. But both companies have access to excellent silicon technology, well, except for Intel's little problems, right? But basically they both have access to excellent technology. Both companies have excellent engineers. There is a significant number of Altera engineers who are ex-Xilinx and vice versa. So there's cross-pollination between the two companies. They have had litigation between them in the past. They seem to have stopped doing that. But from a technological point of view, I would say Altera is probably an equal or very close. Right. The difference is that's the engineering in terms of the ability to design parts.
Sure. Yeah.
What's different is the vision of where to throw those engineers at in terms of what the product feature set should be, right? And I think Xilinx has consistently done a better job of that, right? Which is why they have the larger market share and why they are in domains that Altera doesn't compete in. For instance, Xilinx is very strong in aerospace and defense. I don't think Altera has as strong a position there. Both companies have been very successful in telecommunications in general, both wired and wireless, right? So, certainly for many years, the telecommunication product lines were the dominant product lines, but Xilinx saw that as an opportunity to grow other divisions as well, which is where we now see all this sort of cloud acceleration and automotive and high reliability stuff for defense and space, right? But yeah, I'm biased, but I'm willing to say that the actual engineers are it's not like either company has some superstar that the other company wished they had.
Sure.
Right.
So, like, if we summarize it, it's like worst case scenario, it's a duopoly, and
yes,
the others are lagging quite a bit behind. Duopolies that's not too bad.
Yeah, it actually has been a duopoly pretty much forever. There was never a time that Xilinx or Altera were number one and the other company was number two.
Sure.
So
yeah, but if we, like earlier we concluded maybe we are at an inflection point, and now we conclude maybe we're a duopoly. So a duopoly and an inflection point. I can see why AMD would want to buy Xilinx.
Well, yeah. So the question that is strongest in my mind is how will AMD utilize the Xilinx technology, and how much would AMD change Xilinx's way of doing business in terms of the decision-making process of what products it makes. I kind of went through this thought experiment 5 years ago because several analysts called me up 5 years ago when Altera got acquired by Intel, and they asked me, is this the end of Xilinx? Right? They said, and all I could do was laugh at the time, and it wasn't because I'd had no respect for Altera. I was highly respecting their product. It's an excellent competitor to Xilinx. But I said, look, and this is 5 years ago, I said, at the best, this will be a wash, and at the worst, this will be an excellent thing for Xilinx, right? And my thinking back then was, if Intel lets Altera continue to operate exactly the way it was, it will continue to be a worthy competitor to Xilinx, and it'll be status quo. If Intel screws around with how Altera makes products to tie it into how Intel makes products, that will damage Altera's ability to compete with Xilinx. And so while Intel might end up with something that might be a better product for Intel, it wouldn't be a better product for Altera's traditional customers, right? And so I kind of feel the same way that it depends what AMD does with Xilinx if they acquire them. If they just run it as an independent division, then the question I'd ask is, what's the business case for acquiring it, right? It expands the market, so I guess it affects the top line.
Well, if AMD could do it with shares, it's very beneficial to them.
Right.
If their shares are a bit overvalued, but if the shares are fairly valued, it's a wash.
Right. If AMD decides it wants to change the way Xilinx does business, or how it tells it to abandon circuit markets and go after other markets that might be more in tune with AMD stuff, I would think that would be to the detriment of the value of the acquired Xilinx.
And then I read this articles which said that Intel would try to combine like their CPUs or a CPU with an FPGA on one die. That's how it was explained to me.
Right.
Now, I understand that product's out and it's not super popular or a great success. Is it something AMD could try, and is it feasible? Or
so it actually is the only thing that makes sense. So if you're not putting the chips together on a single piece of silicon, then what you've got is basically you've got a slight integration, right? You've got an integration advantage, right? It's a little bit smaller, but functionally it's not much better than having the two separate products sitting on a circuit board, right?
And so is that what you explained earlier to us, that you've been doing this for years, like putting extra blocks
right
next to
right.